It's my pleasure to introduce Omer from Bogazici University, and he will speak about torsion of rational elliptic curves over cyclotomic extensions of Q.
Okay, so let's start. Thank you for having me. It's a great pleasure to do this presentation, and it's actually like I made this presentation multiple times, but this version is actually the first time I will present, because back then it was only my master's thesis work, but this year I put more effort on it, so I was able to get better results. So this is the first time I will be sharing this updated version. Okay, so let's start. So just for quick reminder for the people, what's an elliptic curve? So in general, elliptic curve can have this multiple coefficients. It's an equation that can be written in this form, but we will be dealing with short Weierstrass form in general. So if the field of the characteristic of the field K is not 2 or 3, then we can put this in the form called short Weierstrass form. So it's just y squared equals x cubed plus ax plus b. And if the coefficients a and b belong to the field K, then we can say the elliptic curve is defined over K. Okay, so it's not, elliptic curves are not just some equations, they are what is called a special type of abelian variety. So we can form some groups. We can define a group operation with the points on the elliptic curve. And for our case, it's just basically take any line. It will intersect the curve in 3 different points. We define their addition of the points as 0, or like the identity element. So that is a group law, and it will give us a group. And when the elliptic curve is defined over K, if we look at the points from K, which means K rational points, which means that the coordinates of the points have their coordinates in the field K. And so it will be closed under addition. So if 2 points belong to EK, which we denote by K rational points, so the third one will also, their addition will also belong to this. So we have a abelian group. And if a very important theorem about the structure of EK is Mordell-Wales theorem, and it says that if K is a finite extension of Q and E is defined over K, then the K rational points EK is finitely generated abelian group. And here it has the so it can be written as the product of torsion part, where the subgroup of points with the finite order and copies of Z. And another important thing about this theorem is the torsion group is itself a finite group when K is a finite extension, and the rank R is a non-negative integer. So, okay. So in general, there's lots of research going on about torsion part. There's also lots of research going on about the rank, and both of them combined all together. But today we will be mostly talking about the torsion, like we will be only talking about the torsion part. And actually, so we will start with a short review, and then we will see what I did and what are some methods that can be used, and etc. So one of the, I guess the most important theorem about torsion groups is Mazur's theorem. And so it says that if E is defined over Q, then the Q rational points, we look at the torsion group, is isomorphic to one of the following groups. So he classified all the possible structures. And also importantly, all of these 15 torsion subgroups appear infinitely often. So appear over infinitely many different elliptic curves. And his result kickstarted a bunch of research on torsion. Lots of people try to imitate his methods, try to expand on his research. So let's check them. Okay, so one following generalization of his result is, okay, due to Kamieni, Kenko, and Momose, So if K is a quadratic field, E is defined over K, then EK torsion is isomorphic to one of the following groups here. And as you can see, so here K can be any quadratic field. So we don't know which one of these subgroups is realized over a specific K or not. They classify for all possible quadratic fields. But importantly enough, so if, for example, mod 4 times modulo 4 is appearing over only Qi, and Z3 times Z3 or Z3 times Z6 appear over only Q adjoint square root of -3. And this is for a reason, because in general, due to something called Weyl pairing, if Zn times Zn is contained in EK torsion for some field K and for some integer n, then we must have the nth root of unity inside the field K. So as you can see, in mod 4 times mod 4 case, fourth root of unity is I, so I must belong to K, and K is quadratic, so it is Qi. And since third root of unity, so you can see Q adjoint minus root 3 is basically the same field as Q adjoint third root of unity. And it is the reason why. So this Weyl pairing also will be an important tool in torsion research, basically. Okay, so another expansion on this classification results, you can see the huge time gap. So it's due to Etropolsky, Morov, Zurich, Brown, and Derricks in 2016. And if K is a cubic field, E is over K, then EK torsion can be only this following groups. And so there's also in literature, when K is quadratic field, it is solved when K has degree 5. I'm not sure, it might be solved in this case also, but the problem is, can we keep doing this? Can we just increase the extension degree one by one and classify torsion over all fields of that degree? And actually the answer is yes, because due to Merrell's uniform boundedness theorem, if K is of degree D, K is a degree D extension, then there's a bound depending only on the extension degree, such that order of EK torsion can be bounded by this BD, this bound. For all elliptic curves defined over K, and K is varying over all such fields. But yeah, so in theory, it's possible. So if the order is finite, there's only finitely many possible structures. So we can just go over them, see which ones are realized, which ones are not, and can do a classification. But the problem is when you extend the degree, it gets harder and harder. It gets more time consuming. The computer calculations that are used getting more time consuming also. So it's a slow progress, but in theory, it's possible. Okay, another variant of the problem we solve is, okay, what if we only focus on the elliptic curves defined over Q and try to understand EK torsion? So in Mazur's theorem, both fields are Q, so there's no such dispute, but
Omer, can I ask you a
sure.
question about
Of
Merrell's
course.
theorem? Is that bound explicit? Can it be made explicit?
Actually, it's good, very good that you asked, because I forgot to tell that. Yes, so that bound is also explicit. There are some bounds already known, and there are some conjectures about that, which can be still proven. But yes, there is explicit bound. So basically, yeah, actually the bound being explicit is important. So then we can actually do classification. Yeah, thank you for asking that. I forgot to mention.
Thank you.
Yes. So another variant of our problem is, what if we only focus on elliptic curves over Q and look at the EK torsion? So Najman classified this for quadratic fields in 2015. And you can see here. So the groups we see here actually, so the problem is a special variant of the other one. And the groups we see will be a subset of the subgroups that we already saw in the other problem. So if E is also defined over K. And for example, you can see that back then, I mean, you can miss that detail, but for example, modulo 16 has appeared as torsion when E is defined over K, but for now, modulo 18 is not apparent. So when E is defined over Q, some of the groups are non-realized suddenly. So it's an important distinction, and also it's actually good to define E over Q because now you can use some special methods, you can use some techniques to help you out, and I will be also talking about those techniques. So here in the same paper, he also do the classification for cubic fields, and still E is defined over Q. Now after on, E will be always defined over Q, so instead of repeating it every time, we can just assume that. So for example, in this one, there's a special property. We already saw some of the group structures appearing only over some certain fields, but in this one, there's an even more special property. So the group modulo 21, it appears only over this field Q zeta 9 plus, so the maximal real extension of Q zeta 9. But it is also realized over only one unique elliptic curve, which has this code you can with the Cremona label, so you can look at in LMFT database. So yeah, it's an important factor. Sometimes some torsion groups appear only over finitely many elliptic curves. And it is for a reason because so one of the important methods used in torsion research is modular curves, and we look at the modular curves and look at their rational points. Sometimes the modular curves, if they have genus 0, they can have infinitely many points. But sometimes they have genus 1, so they are also elliptic curves themselves, so they can have finitely many points, infinitely many points, nor points at all. When I see points, I mean rational points. If they have genus larger than 1, then Falting's theorem say they have only finitely many points, but are they? So yeah, this unique phenomena is due to this fact. So modular curves are very important in this research. And I'll be also using some knowledge about them. Okay. Just a second. Okay. So, okay, what about if we have infinite extensions? So can we find some results about that? And it's also important because now we can't use Mordell-Weil theorem. We don't know if the torsion part is finite now. Or we can't use Merrell's bound because it depended on the extension degree. So in general, the torsion might be an infinite group. But for some specific fields, it is actually finite and we can do the classification. So Fujita's results do this when the field is compositum of all quadratic fields. Similar result is due to other authors. They do the same where the field is compositum of all cubic fields. So sometimes it's possible. We will be mostly, okay, and the fields we will be dealing with is actually, so the general problem is Abelian-Galois extensions. So Galois extensions with Abelian-Galois group. So it is a very large problem. And so one of the tools to study that is actually, so we know that due to Kronecker-Weber, all Abelian-Galois extensions are contained in some cyclotomic field, and maximal Abelian extension of Q is basically Q adjoint all the roots of unity. So Ribet's result is very promising. He proved that if E is over Q, then the torsion subgroup over maximal Abelian extension of Q is finite. And his result is actually deeper. He proves this for all Abelian varieties defined over Q. But it is very promising. We know the torsion has finite order, but still this order can be arbitrarily large. So he didn't put a bound on this. But Okay, luckily for us, recently Cho proved that if E is over Q, then torsion over maximal abelian extension of Q is isomorphic to one of the following groups. So he made the classification. And it is actually the crux of my work. It's one of the pillars. So I'll try to expand on his result. Okay, so there's lots of group. But what it means for us that if now I take any abelian Galois extension of Q, then the torsion over that is isomorphic to one of the following groups. This list is almost identical with his list. It's a little bit longer because this list is just all the subgroups of the groups in Cho's list. Okay, so it is good. So basically the strategy is if we pick a specific field, then if we can eliminate some non-realized possibility structures, then we end up with a shorter list. So we made the classification over any abelian Galois extension, like that we focus on. But the problem itself is very general. So instead, it's better to just focus. For me, it was the time only permitted that I focused on cyclotomic extensions, and even in them, I only focused on cyclotomic extensions in the form of Q zeta P, where P is a prime. Okay. So also one of the important results I get an inspiration is due to Gonzalez, Jimenez, and Nashman. They prove if the K is of extension, K has extension degree n, and n is not divisible by 2, 3, 5, 7, then they prove all the torsion points are actually rational torsion points. And it's very promising because we already know from Mazur's theorem or some other theorems like Nagel-Lutz, it's very easy to find rational torsion. So one strength of their theorem is here K doesn't need to be a Galois extension, which is very strong. But for me, it has a weakness because n is not divisible by 2 is actually very restricting because I want to work with cyclotomic extensions and they will always have even extension degree. So I tried to relax their theorem and actually somehow managed to do it by changing the condition not divisible by 2 into not divisible by 4 and get a similar result. Okay, so here's the main theorem. Okay, we prove that if P is a prime such that P minus 1 is not divisible by 3, 4, 5, 3, 4, 5, and zeta P is the pth root of unity, then the torsion group over QA joint zeta P is one of the groups from Mazur's theorem or one of the remaining 3 groups here. And so yes, so back then when I did this presentation, the condition was always P minus 1 is not divisible by 3, 4, 5, 7, and 11. And this year I managed to use some other methods to get rid of the condition not divisible by 7 and 11. So we will be also discussing that. And also we will see what happens if we relax the conditions. What is the result for all such primes? What happens if P minus 1 is not divisible by only 3, etc. Okay, so let's go to the methods. Okay, let me check my time real quick. Okay. Good. Okay, so a very important method as I use is looking at the effects of Galois actions on the torsion points. So very trivial lemma, if I have a Galois extension, if I have a point in EK, then when I act on it with some Galois action, the point still belongs to EK and the order doesn't change because basically taking P to the sigma is an automorphism of K rational points of E. Okay, so wait. Okay. Also, just a quick reminder for people, quadratic twist of an elliptic curve means that, okay, E has this form, then we take a rational D, we define the D quadratic twist with the equation dy squared equals x cubed plus x plus b. And then if in any field, if root D is contained in K, then we have the isomorphism between the K rational points of E and K rational points of ED, just as taking X and Y to X and Y over root D. So it is also my result was like, it will be heavily involved with quadratic twists. And we will try to get rational points on some, instead of E, some other quadratic twists. But yeah. Okay, so here's we will see the same lemma with the same name multiple times, but basically I wanted to showcase, actually, so there's two methods we can use when we are working with Galois actions. And also I wanted to show you these two approaches, and also like I wanted to show the natural process of, so I proved some lemmas, I proved more stronger lemmas, and so on and so on. So, okay, one of the first lemma, if D is a square-free integer, if torsion over Q adjoint root D is modulo P for some prime, where P is 3 mod 4, then either all my torsion points in E are rational points, or I take the isomorphism, go to ED, and now all the torsion points are actual rational points in D. So in one of them, all points are torsion, and the groups are isomorphic. So it's very good, because in the end, my strategy is, if I can prove all or most of the points are rational, I can use Mazur's theorem and make the classification. So how do we prove this? Just going to quickly. Okay, this one method is working with orbits of...
Sorry, Omer, can you go back to the statement of the last step? So,
this one?
Yes. I see. So for either the elliptic curve or the quadratic twist of it by D, those two are the same. Yeah, I see. Okay, thank you.
You're welcome. Okay, so how to prove this? Okay, so in this method, we work with orbits of points under Galois actions, but we work with orbits of multiple points. So this is one method. In the other lemma, we will work with orbit of single point. So in this, we partition the set of torsion points. We exclude the identity. We partition them into plus P minus P and plus P minus P conjugate. And the conjugation is just here taking root D to minus root D. And since P minus 1 is not divisible by 4, so there's a point P such that his orbit is containing only 2 elements. And since P cannot be minus P, why? Because there's no 2 torsion points. So P must be either P conjugate or minus P conjugate. This means that X is a rational. So X coordinate of P is a rational number. And since X is rational, Y square is rational. So either Y or Y times root D is a rational number. So if Y is rational, P is a rational point, and C, torsion group was modulo P, so it is cyclic, and any non-identity point generates it. So all my points NP are rational points. So all points are rational points. If Y is not rational, then Y times root D is rational. So I do the same on the D quadratic twist, and now the image of P on that curve is rational, so it generates the torsion group. So now I have everything as rational points. So this is one way to use Galois actions. Otherwise, okay, this another lemma I proved is, okay. So take an Galois extension of degree n. Let's say the EK torsion is isomorphic to modulo P for some prime, and also assume GCD of n and P minus 1 is 2. So if the GCD is 1, it's very easy. All torsion are rational torsion, like similar to Najman and Gonzalez-Jimenez result. But if the GCD is 2, then either all torsion are rational on E, Or I take the isomorphism, I go to D quadratic twist, and now all torsions are rational in that quadratic twist. And here, importantly, this D must be, so D is a square free integer such that root D is contained in K, so that I have my isomorphism. Okay. How do we prove this? So that way, like this GCD equal 2 condition is a way to circumvent, like relax that condition, extension degree not divisible by 2. Okay, so now I will only consider orbit of one point. I take a torsion point, it generates the group, torsion group. I act on it. So it must be a multiple of itself because its image is also a torsion point. So it must be a multiple of itself. And okay, let's say it is A. So on one hand, if I apply sigma n times, then basically it is trivial action because sigma's order divides the group of Galois group, order of Galois group. So applying it n times has no effect. Since Fermat's little theorem, a to the p minus 1 is 1 mod p, so applying sigma p minus 1 time also has no effect. And by using Euclidean algorithm, I can show that due to GCD assumption, if I apply sigma twice, then I get the same point, which means that acting on p takes p to itself or it's minus 1. It takes to p or minus p. Either way, it means that the x coordinate of p is always fixed by any Galois action, so it must be rational. And again, y square is rational because of the equation y square equals x cubed plus x plus b. And then either y is rational, if so, p is a rational point in ek. If not, y is, so if not, then the image of my point is a rational point in some other quadratic on some quadratic twist, so I can work with there. Again, P generates the torsion group. It's a rational point, then all points are rational point. Again, if not this work on E, I work with some quadratic twist. So that's again showcasing two ways to use the result, the Galois action. Okay,
sorry, could you go back for a second? Sorry, yeah. So it's the third line when you say that sigma p minus 1 acted on p is p itself. Why is that?
Because so look at the p to the sigma equals ap, right? So what happens if
got it.
Yeah.
Thanks.
You're welcome. It's actually a good question. It's an important idea of the proof. Okay, so one of the main lemma in my proof is basically by using those two results. Well, actually, the previous one. So the previous one can be generalized to not only p, but it can be generalized to power of p. So, and because the multiplicative group still will be cyclic when I change p to the k, and the GCD condition instead changed to GCD of n and phi of p to the k. So it will be p minus 1 times p to the k minus 1. So it still holds. And by using this, we can prove lots of things under lots of conditions. So for example, like if I take a Galois extension of Q, E is over Q. For example, if extension degree is not divisible by 3, then for example, EQA torsion cannot be modulo n for n is 14, 18, 19, 21, etc. So why there is this multiple cases? So basically the same methods of my methods can be used to prove under infinitely many conditions about n to show infinitely many different torsion groups are not realized by I only focus on certain ones because those are the ones that appeared as subgroups of EQ abelian torsion. So that's why eliminating them was important. So basically the previous lemma can be, this is actually continuity of it. So basically you can get rid of a bunch of possible torsion structures. And this one is not possible by the previous lemma. So eliminating mod 2 times modulo 16. under the assumption that an extension degree is not divisible by 3 and 4. This is like the final step. And it can be proven a similar method with the first one we saw, like the partitioning idea. Here, the partitioning is a little bit harder, but not that much. So here we can see, okay, take a torsion point. If it has order 16, and I look at the order 16 points, and since due to my model, short Weierstrass model, there will be 8 different x coordinates. I partition those 8 points into disjoint union. So I make a disjoint union by looking at the Galois orbits, like orbits of x coordinates for different points. And okay, so these 8 elements will be partitioned. And this order of this, if you fix a specific x for some specific order 16 point p, then order of this orbit will be actually the extension degree of qx, and it will divide the extension degree of k. So it cannot be 3, it cannot be 4, it cannot be 6 or 8, because we assume extension degree k of k is not divisible by 3 or 4. Then we look at the possible partitions and see one of these orbits must contain at most 2 points for 2 x coordinates for some p. And then again, so if I add the y coordinates, then there can be also degree 2 extension over that. But each time I use the extension degree is not divisible by 4. So in the end, basically, I also look for the 2 torsion points also, combine them, and I show basically all of the Z2 times Z16 torsion must be contained in some quadratic subfield of K. And then basically it is not possible due to Najman's result actually. Okay. So let's go to the proof of the main theorem. Okay. So in the main theorem, actually the lemma with all these different conditions, if I combine that and also this other one, mod 2, mod 16, then it can actually prove the following. It can actually prove the main theorem under the assumptions p minus 1 is not divisible by 3, 4, 5, 7, and 11. Okay. But how do we remove the conditions not divisible by 7 and 11? So that is this year's work. Okay, before we go, let me check my time. 34, yeah, okay. So let's talk about isogenies. So actually isogenies are morphism between elliptic curves with taking the ident point at infinity to point at infinity. When I say morphisms, they are like algebraic geometric. It has an algebraic geometric definitions. It can be considered as taking x and y coordinate to some rational function of x and y, comma, some rational function of x and y. And okay, but cool thing about them is they will give a group homomorphism between the points of the elliptic curves. Okay, working with different elliptic curves and morphisms is actually very exhausting. So instead of that, we will use this proportion to not work with them, but work with them under some other disguise. So okay, also, one important thing, the kernel of such morphism will always be finite. Then the converse is also true. So if E is an elliptic curve and the bold phi, large phi is a finite subgroup of E, then there's a unique elliptic curve E prime, and there's a unique separable isogeny, which it doesn't mean that much. If field characteristic is 0, it's just any
Omer, I
isogeny.
think in your slide, I think you wanted to say that it's a surjective morphism. Because
True, actually. Oh, yeah. I guess except the trivial one, right?
yeah, you want to say yes, yeah.
Yes, you're right. You're right. Actually, you're right. Yes, yes. So, yeah. Okay, yeah. If it's a Right? If it's like as non-trivial, then automatically it becomes surjective. If not everything is going to O, then
Because
it
you're
is
dealing with
surjective, it
curves,
has
that's
finite
true.
kernel.
Because
I
you're
think
dealing with
it was true, I think.
because you're dealing with elliptic curves, yes. Being non-trivial, because your dimension is 1, then yes. Not being non-trivial would guarantee surjectivity.
Yeah, we get that. We get finite kernel. Yeah, but in general, dealing with them is in this form is ugly. So instead, okay, so if we have a finite subgroup, then we have an isogeny taking from E to E prime, satisfying, okay, with the kernel of phi is bold phi. And even better, if E is defined over K and the subgroup phi is Galois K bar over K invariant, so it's stable, then the isogeny and the curve phi and curve E prime can be defined over K. So we already saw what E prime defined over K means. It's the coefficients belong to K. But the isogeny phi defined over K means that, so remember, an isogeny is not just a group homomorphism. It's like rational function. So if it means defined over K means that those rational functions, coefficients of them, can be chosen from K. So basically, we will be dealing with finite subgroups of E, so they will be torsion groups. And then we will look if they're Galois invariant. Okay. So rational isogenies will carry a significant role in the presentation. When we say an isogeny, we mean that Q rational isogeny with kernel isomorphic to modulo n. So it actually also means a subgroup of E with isomorphic to modulo n, and it should be fixed under Galois Q bar over Q action. Okay, so now an important theorem, it's due to different multiple authors, but Mazur is one of the most, like he contributed a lot and his actual theorem is a result of actually finding rational isogenies. So, okay, if E over Q has an n isogeny, then n is less than 19 or this finitely many cases. If it doesn't have complex multiplication, then the list gets shorter. Also, more importantly, for some isogenies here, so for some of them, if n is like 10 or something, then there's infinitely many elliptic curves. But for some cases, like n is 67, then there's actually finitely many elliptic curves with n isogeny. And actually, we can find those in some tables in other authors' works. And then look at the elliptic curves, search them in LMFT database, and so on. Okay, so if then we saw that if an elliptic curve having an n isogeny is very limiting. So if we can show under certain torsion conditions, then n isogenies exist for some n's, then it is very useful. So looking at isogenies is very important in torsion research, and here's why. Here's an example why. Okay, if K is a Galois extension of Q, E is over Q, and let's say K torsion is isomorphic to modulo M times modulo Mn, then E has n isogeny over Q. So rational n isogeny. Okay, and the proof is very simple. Take any point, act on it. Take any K torsion point, act on it, still a K torsion point. And the multiplication is actually Galois invariant. So like if you act on MP with sigma, then it's just M times P to the sigma. So we can see M times the torsion group is Galois invariant. Q bar or Galois group Q bar over Q invariant. And it is isomorphic to modulo N. We apply the proposition, so E has an isogeny. Okay. Before we go in on how, so actually here at this point, I'm not going into full detail of how I get rid of 7 and 11, but basically, so those conditions back then when I first did my research, they were like they were like sharp. So adding actional conditions didn't bring me anything, but I couldn't also remove them because if I remove 11, not divisible by 11 condition, then modulo 67 can appear as torsion group. And I couldn't get rid of that. But with isogenies, we can get rid of that because if the torsion is modulo 67, then E has 67 isogeny. And from the other work, we know that E can be only finitely many 3 or 4 different elliptic curves. We look at them in databases, see where the 67 torsion is defined, and then we can see, okay, it's not defined in the fields we are interested in. So that's how we get rid of it. But so yeah, basically I won't go into much detail anymore. Another corollary of our work is, so basically we work with finite fields, and it actually helps us to classify torsion over infinite fields, because Guzdwig and Krijan, they prove that if P is at least 5, then the field on the left has the same torsion as Q zeta P torsion. Okay, here zeta P is just P root of unity. This mu P to the infinity means the set of all P power roots of unity. So there's like P power, P squared power, etc. So this infinite extension have the same torsion as Q zeta P. So just the direct corollary. Now we made the classification over this infinite extension. Okay. So relaxing the conditions, I'll just show it is possible. I won't go into detail. So if you remove not divisible by 5, for example, now some new groups appears, modulo 25 and modulo 11 appears, but modulo 11 is only realized when P is 11. So if you remove not divisible, or if you only put P minus 1 is not divisible by 3, then the list gets a little bit longer. And finally, if you remove all conditions and look for any prime, then again, you get a longer list, basically. It is possible, but again, if you fix a specific P, then the problem is much harder than in each specific P, you can make the list very short or not very short, depending on the P. Finally, we will be talking about, let me check my time. Okay. I guess I couldn't make the 45-minute mark, but I guess 50-minute mark will be enough. Okay, the realization of torsion subgroup. So one important result I had was, under certain conditions, I prove all torsion will belong to only the torsion over Q adjoint minus P root of minus P. So it is good because like torsion over quadratic field is somewhat studied. So we can use the results over them. For example, so again, so let's look at mod 2 times mod 10. So these remaining 3
Can
groups.
you go back to the statement, Omer?
Sorry. Yes.
If it's okay, thank you, got it.
I actually missed the word. So it should be one of the groups from Mazur's theorem or these 3. So there's a word missing actually. Yeah, so the groups from Mazur's theorem, they're always there. But the remaining 3, so they can be realized over some prime P's. So they might be not realized over some P's. So in general, we can't get rid of them, but it's also sometimes find some examples with them. So here we will be talking about those. So for example, by using some theorem, special theorem with some models and stuff, here I use lots of some computer code to find mod 2 times mod 10 is realized over Q adjoint my root of minus 59. So with a little bit work, we can also show the torsion over 59th root of unity, Q adjoint 59th root of unity is basically again Z2 times Z10 because it can't be larger. So luckily for some primes, we can see those torsions are realized. Similarly, mod 2 times mod 12 is realized when my prime is 47. Modulo 16 it's very actually hard. So when P is a prime such that in my first version, P minus 1 is not divisible by 3, 5, 4, 5, 7, 11, then there's no example that we know that such prime exists with modulo 16 torsion, but it can exist. Like we can't eliminate that. So at least with my methods. So here's a result of bandwidth and Derek's using lots of computation. They show if D is bounded by 800, it's a square free integer, then if modulo 16 is realized over Q adjoint root D, then D can only be those finitely many values. So in our work, 41 seems promising, so we can have modulo 16 as torsion when we look at the field Q adjoint 41th root of unity. But yeah, so in their work, I couldn't find the elliptic curve, which elliptic curve has this torsion, so also couldn't write it as an example. So finally, we can give some examples where n torsion is realized. So for some n, again, we said that modular curves had finitely many points. So n torsion or n isogenies are also realized over finitely many elliptic curves. And here I present like if my elliptic curve has n torsion over some over some subfield of an cyclotomic field, then those are the examples. Like so those are the examples. And yeah, thank you for listening. I really enjoyed giving you this talk. And yeah, if you have any questions, I'll be happy to try answering them.
Well, thank you.